Welcome to DAR Tutors. Today, we'll explore key chemical principles relevant to IB Chemistry Higher Level. Our focus will be on models of bonding and how these models help us design and understand materials, from metals to plastics. A central question in materials science is, what role do bonding and structure have in the design of materials? The answer lies in understanding the fundamental forces between atoms. Models are fundamental to chemistry. A scientific model is a simplified description that allows us to create explanations and make predictions about the physical world. These models aren't reality. They are useful tools that are modified as we discover new data. Think of it like a simplified map of a complex city. It doesn't show every detail but helps you find your way. For example, the Bohr model of the atom provided a simplified visual of electrons orbiting the nucleus in circular paths. While it's a teaching model that doesn't represent reality, it was a crucial step in understanding atomic structure and is still used today for basic explanations. A key concept we'll use is electronegativity. Electronegativity is a measure of an atom's power to attract electrons towards itself in a covalent bond. Although electronegativity is a theoretical concept influenced by the atom's environment, it is incredibly useful for predicting bond types. The type of bonding between atoms is primarily determined by two factors: the size of their electronegativity values and, more importantly, the difference between these values. A central idea in chemistry is that bonding is not just three distinct types, ionic, covalent, and metallic, but rather a continuum. This continuum can be visualized using a powerful tool called the bonding triangle or Van Arkel diagram. This diagram provides a quantitative way to predict the structure and properties of binary compounds, meaning those made of two different elements. The diagram is a plot with two axes. The x-axis is the average electronegativity of the two elements, which we'll call chi A and chi B, divided by 2. The y-axis is the absolute difference in electronegativity. The x-axis, average electronegativity, gives us an idea of the degree of covalent bonding. The y-axis, electronegativity difference, tells us about the degree of ionic bonding. By calculating these two values, we can pinpoint a compound's position on the triangle and determine the dominant character of its bonding, whether it's metallic, covalent, or ionic. This allows for a more nuanced understanding than just placing a compound into a single category. Let's use the bonding triangle to determine the nature of bonding in a compound. We're given the electronegativity values for phosphorus, which is 2.2, and chlorine, which is 3.2. Our goal is to determine if PCl5 is metallic, covalent, or ionic. First, we calculate the average electronegativity for our x-coordinate. We add 2.2 and 3.2, which gives 5.4. Dividing by 2, we get 2.7. So our x-coordinate is 2.7. Next, we find the difference in electronegativity for our y-coordinate. We take the absolute value of 2.2 minus 3.2, which is the absolute value of negative 1.0, giving us 1.0. Our y-coordinate is 1.0. Coordinate is, now that we have our coordinates 2.7 and 1.0, we can plot this point on the triangular diagram from your data booklet. The diagram shows that the point 2.7, 1.0 falls into the polar covalent region. This means that although PCl5 has some ionic character, its primary bonding nature is polar covalent, where electron density is unequally shared between phosphorus and chlorine atoms. So, we can conclude that phosphorus 5-chloride is a polar covalent compound. This demonstrates how a simple calculation and a graph can reveal complex bonding information. Let's work through another example using a compound with more metallic character, gallium nitride, GeN. Gallium nitride is an important semiconductor. The electronegativity of gallium is 1.8, and that of nitrogen is 3.0. Again, we calculate the average electronegativity for the x-coordinate, 1.8 plus 3.0, divided by 2 equals 2.4, and the difference for the y-coordinate, the absolute value of 3.0 minus 1.8 is 1.2. Plotting the point, 2.4, 1.2, on the bonding diagram, we can see it lies in the polar covalent region, near the boundary with the ionic region. This position suggests that gallium nitride has significant covalent character, but also a considerable ionic contribution to its bonds, as the large electronegativity difference suggests some degree of charge separation. This demonstrates how the diagram can show not just the dominant bonding type, but also the degree to which a substance has a mixture of bonding characteristics. Gallium nitride is a compound with a mixture of strong covalent bonds within a crystal lattice, giving it its semiconductor properties. Now let's turn our attention to alloys. Pure metals are often not ideal for engineering due to their properties, such as being too soft or too reactive. To improve these properties, we create alloys, which are mixtures containing at least one metal. Alloying can significantly enhance a metal's properties. Let's look at some key improvements. First, alloys have increased hardness. A classic example is steel, an alloy of iron and carbon, which is much harder and stronger than pure iron. Second, they can have lower melting points. An alloy called Wood's metal, for instance, melts below 100 degrees Celsius, making it useful in solders for connecting electrical circuits, whereas its component metals melt at much higher temperatures. Third, alloys often exhibit improved corrosion resistance. For example, stainless steel, an alloy of iron, chromium, and nickel, forms a dense protective layer of chromium-3 oxide, preventing it from rusting like pure iron would. These enhanced properties arise from the modification of the metal's internal structure. In an alloy, the different-sized atoms disrupt the regular arrangement of the metallic lattice, creating what we call a disordered lattice. In pure metals, layers of atoms can easily slip over one another, which is why metals are malleable and ductile. However, in an alloy, the presence of larger or smaller atoms locks these layers in place, making the alloy much more resistant to deformation and thus harder and stronger. This change in structure at the atomic level is what leads to the dramatic improvement in macroscopic properties. The alloy's strength and hardness result directly from the disruption of the regular metallic lattice. We now shift from metals to polymers, which are large molecules with very high molar masses. Polymers are formed by joining together many small molecules called monomers through a process known as polymerization. There are two main types of polymerization: addition and condensation. We'll start with addition polymerization. Addition polymerization typically occurs with alkene-based monomers. These molecules contain a carbon-carbon double bond. During this process, the pi bond in each monomer breaks, and the monomers join end to end to form a long chain. Because the double bond is added to another monomer, no other product is formed. Let's consider the simplest addition polymer, polyethene. The monomer is ethene. Ethene has a carbon-carbon double bond. In the presence of a catalyst and high pressure, the double bond breaks, and the ethene molecules add to one another, creating a long saturated carbon chain. This repeating unit, shown in brackets with a subscripton, represents the fundamental structure of the polymer. It's important to remember that these chains can be thousands of units long, resulting in a very high molar mass. Addition polymerization isn't limited to ethene. We can use substituted alkenes as well to create polymers with specific properties. Your data booklet contains a table of common addition polymers and their monomers. For example, chloroethene polymerizes to form polychloroethene, more commonly known as PVC. Its properties are very different from polyethylene due to the presence of chlorine atoms. The CCl bonds are polar, leading to strong dipole-dipole forces between chains. Also, the bulky chlorine atoms restrict the movement of the polymer chains, making PVC much harder and more rigid than polyethylene. Let's apply this knowledge to a worked example. Consider this complex addition polymer chain. First, we need to deduce the repeating unit. By inspecting the chain, we can identify a repeating block of atoms. In this case, it's a two-carbon chain where one carbon has a hydrogen and a methyl group, and the other has a fluorine and a chlorine atom. So the repeating unit is CH-CH3CFCl. To find the monomer, we convert the single bond within this repeating unit back to a double bond and remove the bonds connecting it to other units. The resulting monomer is 2-chloro-1-fluoro-1-propene. Finally, why is this not a hydrocarbon? By definition, a hydrocarbon contains only carbon and hydrogen atoms. Since this polymer contains fluorine and chlorine, it cannot be classified as a hydrocarbon. This analysis highlights the power of structure-property relationships in polymer chemistry. A quick call to action. If you're looking for expert tuition in IB A-level or IGCSE curricula, please contact DAR Tutors. Let's explore another crucial class of polymers, condensation polymers. Unlike addition polymerization, condensation polymerization involves the bonding of monomers with the elimination of a small molecule, such as water or hydrogen chloride. This process requires monomers that have at least two reactive functional groups, one at each end. When these groups react, they form a new bond and release a small molecule. Let's consider a well-known example, the formation of nylon 6,6. The two monomers are 1006-diaminohexane and hexanedioic acid. The amine group on one monomer reacts with the carboxyl group on the other. The hydroxyl from the carboxyl group and a hydrogen from the amino group combine to form a water molecule, which is eliminated. This creates a new amide linkage between the two monomers. The result is a repeating unit where an amide bond, or peptide bond, connects the residues of the two monomers. Another important type of condensation polymer is a polyester, like polyethylene terephthalate, or PT. Here, a diol with two alcohol groups reacts with a diacid with two carboxyl groups. Water is again eliminated, forming an ester linkage. The formation of this ester link by removing water is the characteristic condensation reaction that builds the polyester chain. Both polyamides and polyesters form strong intermolecular forces, called hydrogen bonds, between their chains, which contributes to their excellent physical properties like strength and high melting points. The physical properties of a polymer are also strongly affected by its structure at a larger scale, known as its microstructure. We can categorize polymers into two main types based on their response to heat: thermoplastics and thermosetting polymers. Thermoplastics are made of long, linear or branched polymer chains that are not covalently linked to each other. They are held together only by weaker intermolecular forces like London dispersion forces and dipole-dipole interactions. Because these intermolecular forces are relatively weak, they can be overcome by heating. This allows thermoplastics to soften and flow, so they can be molded into different shapes and then harden again upon cooling. This makes them recyclable. Examples of thermoplastics include polyethylene and polychloroethylene, or PVC. On the other hand, thermosetting polymers have their chains held together by strong, permanent covalent bonds, forming a three-dimensional network structure. This process is called cross-linking. Once formed, these covalent crosslinks are extremely difficult to break. This means that thermosets will not soften or melt when heated. Instead, they will eventually decompose. They cannot be reshaped or recycled. A well-known example is vulcanized rubber, where sulfur atoms form covalent crosslinks between isoprene chains, making it much stronger and more durable than natural rubber. Another important aspect of polymer microstructure is crystallinity. Some polymers, like polyethylene, can have regions where the chains are closely packed in an ordered parallel fashion. These are called crystalline regions. However, most of a polymer's structure is amorphous, with the chains randomly entangled. A polymer often contains both crystalline and amorphous regions. The ratio and arrangement of these regions greatly influence its macroscopic properties. A higher degree of crystallinity usually results in a denser, harder, and more opaque material. Let's conclude by tackling some IB-style practice questions to reinforce these concepts. First, use the bonding triangle to determine the nature of bonding in aluminium iodide, AlI3. Electronegativities. Al equals 161, I equals 2.66. Take a moment to calculate the coordinates and plot them. The average electronegativity is 2.14. The difference is 1.05. The coordinates 2.4 1.05 fall in the polar covalent region. So, aluminium iodide is best described as polar covalent, consistent with its molecular structure in the gaseous phase. Next question. Draw the monomer for this polymer. How do its properties compare to polyethylene? First, identify the repeating unit, then convert it back to the monomer. The repeating unit is CCH3-2. The monomer is 2-methylpropene. This polymer, poly-2-methylpropene, has stronger London dispersion forces than polyethylene due to more electrons, leading to a higher melting point. Question 3 asks us to distinguish between thermosetting and thermoplastic polymers. Remember, the key difference is the type of bonding between chains. Thermoplastics are made of chains held together by weak intermolecular forces. They can be melted and reformed. An example is PVC. Thermosets have chains joined by strong covalent crosslinks, forming a rigid network. They decompose when heated. An example is Bakelite. Question 4. Draw the repeating unit of the polymer formed from the condensation reaction of propanedioic acid and ethanediol. Identify the functional groups involved and the molecule that is eliminated. Propanadioic acid is a diacid, and ethanediol is a diol. The carboxyl and hydroxyl groups react to form an ester bond, eliminating water. The repeating unit will be an ester linkage followed by the remnants of the diol, another ester linkage, and the remnants of the diacid. Our final question is about the properties of alloys. Remember the concept of the disordered lattice. Pure metals consist of a regular repeating lattice of atoms of the same size. This allows layers of atoms to slip easily over one another, making them soft. In an alloy, atoms of different sizes disrupt this regular arrangement. This creates a disordered lattice. When stress is applied, these different-sized atoms act as obstacles, preventing the layers from slipping past each other. This makes the alloy much harder and stronger. Today, we've seen how models like the bonding triangle provide a quantitative way to understand chemical bonding. We've also explored the structure and properties of alloys and polymers, demonstrating how we can design new materials for specific applications. Thank you for your attention. This lesson has been brought to you by DAR Tutors. For personalized expert tuition in IB Chemistry HL or any other IB A-Level or IGCSE subject, please contact us. Our tutors are dedicated to helping you achieve your academic goals.